Today we're going to be talking about Extrema. So we've talked about Extrema a little bit already, obviously with the extreme value theorem. We've talked about kind of here and there in mathematics. But Extrema are minimum or maximum y values on a function. We have lots of different types of Extrema. We have absolute Extrema, global Extrema, endpoint Extrema, relative Extrema, and local Extrema. Now some of them can kind of be grouped. So absolute and global, they're basically the same thing. Okay, and they mean the highest or lowest maximum or minimum on the interval / function. So the absolute highest max, the absolute highest min, that's our absolute or global. Okay, relative or local is any max or min that occurs on the interval function at critical points or numbers. So any spot where we have a little, bump or we have a little valley, those are going to be your relative or your local max and mins. And absolute and relative are going to be the words you see referred the most, but you will see global and local every once in a while. And then endpoint Extrema is just anytime we have a max or a min at an endpoint, because sometimes you could have your endpoint at what is a true max or min, but also sometimes because of where the interval cut off, we end up with a max or min when it wouldn't necessarily be a max or min on the function normally. Okay, now let's talk about what is a critical number. So let f be defined at c if f prime of c is equal to 0, so that means that the derivative is equal to 0, or if f is not differentiable at c, or if I can't take the derivative, then c is a critical number of f. And critical numbers are where Extrema happen. So it's very important that I can find critical numbers, because if I can find critical numbers, then I can find Extrema. Okay, so there's an example of two spots. So one is where the derivative would not exist, because from the left and the right, I'd do that jump. Okay, it's that sharp point or cusp. So that would be a critical number c, and you can see that we have that maximum occurring there. Okay, and then here we have our horizontal tangent. The derivative is equal to 0, and once again, that would be at a maximum. Okay, so c is the x value where the critical number occurs. F of c would be the actual value of the maximum or the minimum. Okay, so let's go look at an example. So we want to find the absolute extrema of f of x is equal to 3x to the fourth minus 4x cubed on the interval -1 to 2. Okay, so to find the absolute extrema, first thing I need to do is I need to take the derivative and find all my critical numbers. Okay, so f prime of x would be equal to 12x cubed minus 12x squared. Okay, then remember, we have critical numbers occur at two spots: when the derivative is equal to 0 or when the derivative is undefined. Now, obviously, to find when the derivative would be equal to 0, we just set the function equal to 0. For derivative being undefined, we want to look for asymptotes, holes, that sort of stuff. This is a cubic function. There shouldn't be any holes or asymptotes or anything like that, so we should be fine. You really only have to worry about undefined when you have some sort of piecewise situation going on, or if you have a function where you know that it should occur. Okay. So set this function equal to 0. So 0 is equal to 12x cubed minus 12x squared. Factor out an x squared and a 12 from both. So 0 is equal to 12x squared x minus 1. Okay. And then we get the x values: x equals 0 and x equals 1. Okay. So now I want to find the absolute extrema. To find the absolute extrema, I need to actually plug in all these different x values. And the x values I can plug in, I'm going to plug in the critical numbers. But because I'm talking about absolute extrema, I'm also going to plug in the endpoints. So we only plug in the endpoints when we're talking about absolute extrema. And I want to know the values of these points so that I know if they're maximum or minimum. So I'm plugging them all into my original function. So I want to find f of -1, which is an endpoint, f of 0, f of 1, and f of 2. I'm going to give you all a couple minutes to plug these in, so you can pause me and then unpause me when you get done. So now looking at all these values, these are all y values on my interval, -1 to 2. So at 1, -1, that would be our absolute min. And we can just abbreviate ABS-MIN. We don't have to write it all the way out. And then 7, 0, 16. 16 would be our absolute max. So as you can see, one of our absolutes happened at our critical number. So at the number 1, we had an absolute minimum. But one of our absolutes happened at an endpoint because at 2, we had our absolute max. So I'm telling you right now, y'all, pretty much every time you get a question that asks you about absolute extrema, one of your absolutes is going to be on the endpoints because that's what they're really testing you. Is they're seeing if you can remember to talk about your endpoints. So let's look at number 2. F of x is equal to x to the 4th minus 2x squared. We're going to find all values on negative 2 to 2 such that f prime of c is equal to 0. So we're finding the critical numbers. So once again, how do we find the critical numbers? Derivative, set the derivative equal to 0, or look for when the derivative is undefined. So first step is our derivative. So f prime of x is equal to 4x cubed minus 4x. Okay, then once again, I want to set this equal to 0. So 0 is equal to, I can factor out a 4x. So x squared minus 1. So that gives us 0 is equal to 4x, x plus 1, x minus 1, which gives us the x values 0, negative 1, and 1. And just to check, okay, on this interval negative 2 to 2, okay, so all 3 of my values do fall in my interval. It's important because sometimes they'll give you ones or they'll cut off the interval in a way that one of your critical numbers or some of your critical numbers won't show up in the interval. So you do need to check that. Okay, so that would be that for finding critical numbers. Okay. On number 3, we have f of x is equal to 5 minus 4 over x. Okay, and we want to find all the values on 1, 4 such that the derivative is equal to 1. F prime of c is equal to 1. Okay, so same thing, we're going to be taking the derivative, but then instead of setting it equal to 0, like on number 2 and number 1, we're going to set it equal to 1. So that's not too bad. Okay, so our derivative, let's see, make this a little bit of an easier function to derive first. So f of x is equal to 5 minus 4x to the negative 1. Change that to a power rule. So now f prime of x is equal to 0, negative 4, negative 1x to the negative 2. So that means f prime of x is equal to negative 4 and negative 1 cancel out. So 4, x to the negative 2 goes to the bottom. So 4 over x squared. Okay. Now I want to know when this is equal to 1, not when it's 0 or undefined. If it was 0 or undefined, I would say, well, 0, because 0 would make it undefined. But I want to know when it's equal to 1. So 1 is equal to 4 over x squared. Multiply the x squared over. We get x squared is equal to 4. Take a square root, take a square root. And we get x is equal to positive or negative 2. Now, once again, we want to check our interval. So we want to find all values on the interval 1 to 4. So that's 1 all the way to positive 1 all the way to positive 4. Negative 2 would not be included in that. So x is equal to just 2 would be our only answer. So see, checking the interval is important. Hey, now before we finish up notes today, y'all, I do just want to talk briefly about all these questions because all of them actually came from conclusions. The way we could do this math and know this math is true is they came from conclusions of some of the theorems that we just did. So up here at the top on number 1, we wanted to find the absolute extrema of f of x is equal to 3x to the 4th minus 4x cubed. Well, that function is a continuous function, and we wanted to find absolute extrema. The reason why we knew the absolute extrema occurred on that on that continuous function is because of the extreme value theorem, EVT. So this is a question that uses the extreme value theorem to find absolute maxes and absolute mins, because any interval on a continuous function will have a maximum and a minimum. Okay, pretty crazy, right? All right, number 2, we wanted to find all the values on negative 2 to 2 such that f prime of c is equal to 0. Now, we don't always have to have this result to be able to find critical numbers. We can find critical numbers for any function by deriving it and setting it equal to 0 or finding when it's undefined. But I do just want to show you that if we were to plug this in, so f of 2 would be equal to 8, and f of negative 2 would be equal to 8. So our y values of our endpoints are the same. Our function is continuous, and it's differentiable because we took a derivative. Okay, so this would actually be Rolle's theorem that guarantees us these critical numbers. Okay, so continuous function, differentiable function on the interval, and starting and ending y values are the same. So we knew we were going to have critical numbers on that interval. So that's pretty cool. And then last but not least, f of x is equal to 5 minus 4 over x. We want to find all the values such that f prime of c is equal to 1. So fun little fact, if we checked our f of b minus f of a over b minus a, so if I did f of 4 minus f of 1 over 4 minus 1, then you would get 4 minus 1 over 4 minus 1, which equals 3 over 3, which equals 1, which is our average rate of change. A, and they gave us an instantaneous rate of change. So what theorem tells us that AROC and IROC are equal on the interval? Well, that is, of course, MBT. Okay, so all of these questions kind of follow from some of our theorem conclusions that we're working with in 4.2. But that's it for today, y'all.